chain rule, where you can sort of like chain entropy together to get it down. And this is all like kind of high level and hand wavy, but we will at the technical detail soon. Yeah.
So for those of you watching online, sorry about the audio before. It should be working well now. Um, Not to insult Jeffrey, but I don't think he mentioned too much yet. We're about to get into um, the meat of everything.
Yeah. Yeah. Okay. So let's talk about how entropy is actually defined. Before I give you the definition, let's talk a bit about how it should be defined. So remember, I said at a high level, entropy is trying to measure the expected amount of surprise caused by a realization of X. So the first thing we want to do sort of is like mathematically define what surprise is. So the surprise of an event occurring, it should really just depend on the probability of that event occurring. So we're going to define our surprise function f, which takes as input a probability, and then it returns how surprising that event is, that probability. And for S to behave well mathematically, we want it to have certain properties. So if I have a certain event, then there's no surprise there. So the surprise of that should be 0. If I have two events and one is rarer than the other, then that rarer event should induce a greater surprise. We want the surprise to vary continuously with the probability of the event. And if I have two events, two independent events with probability P and Q, then the surprise of both of them occurring should equal to the surprise of one event occurring plus the surprise of the other. And keep in mind this is for independent. And the fifth one, it's saying that for an event with a 50-50 chance of occurring, I want the surprise of that to be 1. That's sort of arbitrary, but what it means is that we can say that the unique function satisfying all its properties is exactly the negative log-based theory of the probability. Or, if you report out log laws, this is exactly the log of the inverse of the probability. So note that by taking the inverse of the probability, as the probability decreases, the surprise will be greater. And the fact that we're taking the log of it means that it behaves additively rather than multiplicatively. Okay. So now that we know how surprise should be defined, this is the definition of entropy. So if I have a discrete random variable which takes on these values or these probabilities, its entropy is defined as such. So it's basically the weighted sum of these surprises. And what you'll notice that it depends purely on the probabilities of the outcomes and not on the values of the outcomes. And if we recall our previous surprise function, we see that this formula here is really just the expected value of the surprise of our random variable. Any questions about the definition? Okay. So we'll walk through some examples now, just to really internalize this. Remember, it's just the sum, or it's just the expected value of the surprise. Okay. So let's calculate the entropy of a fair coin. So for a fair coin, there's only two outcomes, each occurring with probability half. So if I just plug this into my formula for entropy, it returns 1. And since we're defining entropy in terms of log base 2, this gives entropy in terms of bits. You could use a different base for the log. I mean, it's not too important. But the fact that we're using log base 2 just means that our entropy is measured in bits here. And the fact that the entropy of this random variable is 1 bit, it tells you that from an information theory point of view, observing the value of this random variable gives you, on average, 1 bit of information. Okay, let's look at another example now. Here I have a biased coin, which gives you heads 90% of the time and tails 10% of the time. If I plug those values into my entropy formula, then I only get 0.69 bits, which is noticeably less than the fair one. So even though observing a tails is very surprising now, since it only occurs 10% of the time, the system as a whole is more predictable because you will get heads almost all the time. So it has less entropy. And we can use, I want to remind everyone that entropy measures the average uncertainty of a random variable. Okay, and then one more example of the coin. This is sort of a trivial example. But if I have a coin with two heads, then its entropy is given as above, so there's 0 bits of entropy. And here the convention is that we treat 0 log 2 0 as equaling to 0. And this result, it makes sense because there can be no surprise when you flip a coin with two heads. So the entropy is 0. But what these three examples illustrate is that the entropy is maximized when each of the possible outcomes are equally likely. And we have this inequality here between the entropy of a random variable and the set of possible outcomes for that random variable. So just a reminder here, SOC means the support of X, which is just the set of outcomes that can occur with positive probability. And we have equality when X is sort of uniformly chosen from its set of possible outcomes. And this is actually one of the key properties of Shannon's definition of entropy, and it proved very useful in the following slides. Okay, so when it comes to combinatorics, we're not actually trying to calculate the number of bits of a random variable. We're trying to get bounds on the entropy of a random variable. And the key link is what we saw earlier in the big picture slide. The key idea is that if I define my random variable x as uniformly randomly chosen from my family of combinatorial objects, then we have this direct relationship between its entropy and the size of our family of combinatorial objects. And with this relationship, any bound we obtain on entropy will imply a corresponding bound on the size of f. And can someone tell me what happens if x is not uniformly chosen from f? Anyone want to take a guess? So basically, when I have equality, if I have an upper bound on entropy, then I have an upper bound on the size. If x is not uniformly chosen from f, then I only have a less than or equal to here, which means that the upper bound on my entropy will not automatically turn into an upper bound on the size of my family. So that's why it's important for us to choose x uniformly from f. Okay. So the question still remains like, how do we actually bound the hx? And why would it be easier to try to bound hx instead of directly trying to bound the size of my family? Okay, so we'll move on to the entropy toolkit next. Does anyone have any questions on what we've discussed so far? Okay. So in practice, so far we've only looked at the entropy of a single random variable, but in practice, what we often look at is the entropy of a random vector, and this itself is just a random variable, and its probability distribution is just the joint distribution of its coordinates. The entropy of this random vector, it's basically the same formula for the entropy of a single random variable, except here the probability of a particular realization of that random vector is just given by this joint probability here. So for example, if my random variable, it could be like maybe x1 is the temperature tomorrow, maybe x2 is the humidity, extreme could be whether it's raining or not, and so on. Okay. The first property that we have is this notion of subadditivity, which means if I have a random vector x1 or xn, then its entropy is at most the sum of the entropy of its components. And equality holds here if and only if all the component random variables are mutually independent. And what subadditivity is saying is that the average surprise of observing each coordinate random variable separately cannot be less than observing all the coordinates together. Okay, so let me give you an example now. Let's say I have two random variables. The first random variable tells you like the total mass of all these objects that I have. The second random variable tells you the number of objects that I have. Well, if I know the total mass is quite large, then I'll be less surprised when I find out there's also a large number of objects. So in this way, if there's dependence between the random variables, then the joint entropy is less than the sum of the entropies of each random variable separately. Another way of thinking about this is that when you have the random vector, you're sort of finding out all of the values of each component at the same time, for like one right after the other. Whereas with subadditivity, you're finding out the values of each component random variable, but every time you see one, you've already forgotten about the previous values. So each time you see a new one, it's very surprising. Any questions about this? Yeah, and then we omit the proof for now, but this will actually follow as a special case on our next result. Next result is Shearer's lemma. So subadditivity, it gives us a bound for the entropy of a random vector, but the problem is that this bound can be quite coarse. Shearer's lemma gives you a generalization of subadditivity, but it's also better than subadditivity in certain cases. So this looks quite complicated, but I'll walk through an example shortly. And this F here, this F, it's not our family of combinatorial objects. This is just a family of coordinate subsets. Okay, so maybe I'll do a little example on the board. So suppose I have a random vector with 3 random variables, and then suppose my coordinates, my family of coordinate subsets, look like this. So each of these translates into something like this. With this set of subsets of coordinates, you'll notice that each coordinate, for example, is coordinate 1. It's included in 2 of these families. The coordinate 2 is included in 2 of these subsets. And same the coordinate 3 appears in 2 of these coordinates. So here R is 2. And what this is saying is that 2 times the entropy of my random vector is at most the entropy of x1 x2 plus x2. So each of these coordinate subsets, they induce a certain projection or local view of our original random vector. And if each of the coordinates in my original random vector is covered in at least R of the views, then what it's saying is that I have at least R times the R copies worth of information. Yeah. And I believe I have an example here. Okay. So let's look at an example now. So suppose I have a coin and then I flip it, and then I define three random variables x1, x2, x3 to all correspond to the same coin flip. So these three events are completely dependent. Okay, then I know that my random vector here has entropy of only one bit because they all correspond to the exact same coin flip. If I use just subadditivity, then I can say that the entropy of this random vector is at most the sum of each individual entropy, which is at most 3. If I use Shearer's lemma with these three local views, then I can say that 2 times the entropy of my random vector is at most the sum of these three entropies. And again, since all these random variables are completely dependent, each of these has an entropy of 1 bit. So this would imply that entropy of my random vector is 302. So it's a bit of a silly example, but the point is that Shearer's lemma can give you a better bound than subadditivity. Yeah.
So is subadditivity just the spectrum base of Shearer's lemma?
Yeah, it's basically Shearer's lemma, where if we look back at here, your family of subsets is just each individual coordinate. Yeah. Any other questions? Yeah. So yeah, that's why Shearer's lemma is like a generalization of subadditivity. But as we also saw, it can give you something better with subadditivity. And we will prove Shearer's lemma later in the free variable case. Okay, next up, I want to talk about this notion of conditional entropy. And it tells you when you have 2 random variables, after you reveal the outcome of one random variable, how much surprise is there remaining for the other random variable. So to do so, first define the entropy of x given some event e. And it's just the entropy, it's like our entropy formula, except now our probability is the conditional probability on e. And then once I have that defined, I can define the entropy for x given y, where x and y are both random variables. So I'm taking the expectation over y for the entropy of x given every possible value or every possible outcome of y. That. Any questions about this formula? Well, I'll give some more examples later, but having defined conditional entropy, the main tool that we have to deal with it is this notion of the chain rule. So if I have 2 random variables, if I have a random vector x, y, then its entropy is the entropy of x and the entropy of y given x. So first I observe x, and then the remaining uncertainty I have in y is its entropy given x. And you can and there's a generalization of the chain rule where when you reveal the next coordinate, you condition on all the previous coordinates. Yeah, let's give an example. So suppose I roll an 8-sided die, and I let x be the number roll, and I let y be the parity, so whether that number is odd or even. So 8-sided die, it's clear that the entropy of the number roll is just 3 bits, because 2 to the 3 is 8, and the entropy of y is 1 bit. Because whether an 8-sided die, the outcome is odd or even, it's sort of like a coin flip. Okay. So let's suppose we first observe x, so the actual number that's rolled. Well, if I know the number that's rolled, then automatically I know whether that number is odd or even. So by the time I observe y, there's no surprise left anymore. I already know the value. So by the chain rule, I can see that this random vector has 3 bits of entropy. On the other hand, if I first observe y, so this tells me, so now I know whether the number is odd or even. And when I know that, then this halves the possible outcomes of the dice roll to only 4 possible outcomes, which corresponds to 2 bits of entropy, because 2 to the power 2 is 4. And the entropy of my random vector, well, it's a symmetric quantity. If I first observe y and then I observe x, I again get 3 bits. And just for reference, I could also try using subadditivity, but subadditivity would only get me an upper bound 4 bits. Any questions about this example? Yes. No, it turns out it doesn't matter. So when you have like a random vector, like a bunch of random variables bundled together, the order in which you learn the outcomes of the random variables as a whole, it will still give you the same surprise overall. So in this case, whether you observe x or y first, your overall surprise will be the same. Okay, and then we can try to prove the chain rule here. I'll only prove the 2 variable case, and then the general case you can prove using induction. So this first part, I'm just applying the definition. And here I'm using the multiplication rule. I know that the probability of xy is the probability of x multiplied by the probability of y given x. And then I'm decomposing my sum. And then here, in that right summing, I'm just adding this sum py given x term. And since I'm summing it over all y, this is really just equal to 1, so I'm allowed to move this. Once I do that, I factorize out my px. And then the inside here, you can like cancel out terms to get this. And this is just the definition of the entropy of y given x. But it's okay if you like didn't follow all the steps. So it just basically follows from the definition and a bit of algebraic manipulation. Okay, and then one last property I'll talk about before we start looking into some of the actual applications is this notion of drop-in conditioning. And the point is that if I know y, then on average this can't hurt me. As in, if I know more information, then it shouldn't make something more surprising on average. Okay, note that I say on average there. Okay, so for example, if x is whether it's snowing tomorrow and y is the temperature, then I'll be very surprised that it's snowing tomorrow if the temperature is like 40 degrees tomorrow. Okay, so in that case, it might actually hurt you. But remember, entropy is a statement about averages. So knowing the outcome of y or z here on average should not increase our surprise when observing x. Any questions about drop-in conditioning? Okay, and then we can prove it too. So this first part is just the definition of the entropy of x given y. And then I can use, well, I write multiplication, we can also call it Bayes rule or whatever, to change it from, so that the probability of x and y is the probability of y multiplied by the probability of x given y. And you can like sort of swap the order of that. And the next part is a bit trickier. Well, I know that my sum of py given x over all y is 1. So I can apply Jensen's inequality to turn this expectation of log, I can upper bound it with the log of the expectation. And then this fraction inside, I can simplify it using a variable. And then ultimately I get the entropy of x. Okay. And now we'll prove Shearer's lemma, and that'll be the last part of the entropy toolkit. So what you'll notice is that really we didn't introduce that many tools. We had subadditivity, Shearer's lemma, chain rule, and dropping conditioning. But with those 4 tools, we'll see that we can prove some very interesting results in combinatorics. Okay, but let's prove Shearer's lemma first in the free variable case. So that's what it says. So by the chain rule, I can split my entropies into entropy of x plus entropy of y given x, entropy of x, entropy of z given x, entropy of y, entropy of z given y. And then I'm applying dropping conditioning, but sort of in the other direction, so I can add conditioning and then change the sign of the inequality. So let's have a look here. So I have a hy here. I can lower bound it by hy given x. I have a hz given x. I'm going to add a conditioning on y. Hz given y, I'm going to add conditioning on x. That's how I get this. And then if I apply the chain rule again now, so this plus this plus this, I get the entropy of my random vector x, y, z. And the general case, the proof of the general case is similar, it just requires a bit more bookkeeping. Okay, any questions before we move on to the application? Okay. Let's look at some applications. So my plan is to look at 2 major applications of entropy in combinatorics. The first one is the Loomis-Whitney inequality. So let me describe the sort of problem here. So suppose you have some 3D solid and you want to estimate its volume. The problem is you can only measure the area of its 2D shadows. How can you use those to bound the size or bound the volume of your solid? And more generally, it's a question of given a n-dimensional body in Rn, you want to estimate its volume, so you only know the volume of its n-1 dimensional projections. Well, what the Loomis-Whitney inequality tells you is that the volume of your n-dimensional object is at most this product here, where each bj is a n-1 dimensional projection of your object. I'm assuming the hyperpoint x shape is associated with dropping the j coordinate basically. Don't worry too much about this. The first point gives you the sort of intuition for the problem that if you want to estimate 3D objects, but you only know the areas of its shadows, how can you estimate it? And it turns out this sounds actually tight. So if these are axis-aligned hypercube or rectangular box, for example, what I want to focus on is the sort of discrete version of this problem. So instead of a solid, I have a finite collection of points in space. So for example, maybe I have a bunch of points in 3D space, and I can only look at the shadows that those points cast, and I want to estimate how many points I have in 3D space. Okay, so now if F is my collection of points in dimensional space, and I let the pi I of F denote the projection obtained by deleting the I coordinate, then we have this sort of discrete version of the Loomis-Whitney inequality. I'll give an example shortly because this does seem quite abstract at the moment. Yeah, and the reason I introduced this problem is because it turns out that we can prove this very easily in fact using Shearer's lemma. But first, let's look at an example. Okay, so now I have my points in 3D space. I had an example in 5D, but I couldn't, represent it nicely on this 2D plane, But basically, I had this cube, I'm imagining I have like the corners of a cube, these are axis aligned. And I'm missing this top right corner. Okay, and then let's try to apply the Loomis-Whitney inequality. So XY projection, if I'm looking down, then I'll see 4 points. If I'm looking XZ, it's XZ. If I'm looking this way, I still see 4 points. And if I'm looking YZ, so if I'm looking this way, I still only see 4 points. So if I plug in these numbers into my previous inequality, what I will get is that the size of f is at most 8. Okay, so we know that obviously the true size of my set is 7, but the problem is that this missing corner, it's sort of invisible in every two-dimensional projection. Any questions about this? Yeah. Okay, so, and now we'll try to prove it. Okay, so I'm going to choose my random vector x1 dot 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 xn uniformly randomly from F, and here each of the xi's just corresponds to, if you recall our F here is a subset of the product space of these n spaces. So the xi is just a random variable that tells you the value of ai. And we will apply Shearer's lemma with these coordinate sets. Okay, so let me draw how this might look. So let's say I have this thing here, 1 to n. That's my original random vector. And then my local views or projections, they'll look like this. So this is n minus your first coordinate, and so let me sort of remind us what's happening here. So I have this random vector on n coordinates, and I'm trying to estimate its entropy. But I can only tell you if I only know the entropy of the projections. So I know the entropy of this, for example, this, and so on. And the key observation is that for any particular coordinate, it appears in n minus 1 of these projections. So for example, this first coordinate, it's missing in my first projection, but then it appears in every other one. In general, the ith coordinate is going to be missing from my ith projection, but it will appear in every other projection. So that's why I can apply Shearer's lemma with r equals n minus 1 to obtain that. Any questions about this? And then the result shortly follows. But the idea again, and just recap, is that I want to bound the entropy of this random vector, but I only know the entropy of its projections. So if I cover each coordinate of my random variable with n minus 1 projection, then I can apply Shearer's lemma with the n minus 1 to obtain that inequality. Yeah. And then if you recall, the entropy of since I chose my x uniformly random from my family, then I know that its entropy is equal to the log of the size of my family. And moreover, if you recall our bound, we had an inequality here. The entropy of each projection is at most the log of the size of that projection. So if I combine these inequalities and then I take the exponential on both sides, then I recover the discrete Loomis-Whitney inequality. And again, the main idea, since every coordinate appears in all but one shadow, together they collectively contain at least n-1 copies worth of information in the original point. So basically, like for this point, for example, I have like n-1 copies worth of information about that point. Any questions about this example? Okay, the next example, this is where things get a bit more complicated, is the proof of Bregman's theorem. So to prove, or to state Bregman's theorem, first I have to introduce this notion of the permanence of the matrix, or the matrix. And the permanent, it's calculated like the determinant, but you know in the determinant you're like adding and minusing things. In the permanent, you're only adding things. Okay. So for an n by n matrix A, its permanent is given by this formula. So, okay, that seems a little scary, but let me explain what's happening here. So, sigma here is a permutation of numbers from 1 to n. And, okay, there's a few ways of thinking about this. So, for example, let's just say I have a 6 by 6 matrix, and in my permutation sigma, it maps my, let's say it was something like that. So this tells me for this permutation, I'm adding the entry in the first row and third column. I'm adding the entry in the second row and second column. I'm adding the entry in the third row and first column. So I have a 6 by 6 matrix. So I'm taking this one here, this one here, 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 for example. So basically, the sigma tells us for each row in the matrix which column you want to like sort of match with, and then you take the value in that row and column and you add it all together. The fact that it's a permutation means that each column is used exactly once. Another way of thinking about this is that imagine you're trying to place like n rooks on a chessboard such that they don't hit each other. So remember, a rook can only move like this. So imagine you're trying to place like n rooks on a n by n chessboard such that they don't hit each other. And then for each of those valid placements, you add the entries where the rooks sit on. That's another way of visualizing it. The point is that the determinant, you're going to be either adding or subtracting this product. So I think I'll say add, but you're taking the product of those entries. The point is that the indeterminate, you're adding or minusing depending on the sign of the permutation, whereas for the permanent, you're only adding. Another way, which might be a bit more natural for some of you, is that I remember for the determinant, like we could like expand along a row where for each like entry in that row, you sort of like delete it, and then you look at the determinant of the submatrix. And then remember when you're calculating the determinant like that, you're adding it and minusing and so on. But for the permanents, you can calculate it in a similar way, except we're only adding. Okay? So like sort of like you might be thinking like, okay, what is the point of the permanent then? Because we know that for the determinant, if you view your n by n matrix as a linear map on Rn, it tells you the scaling factor that it does on the volume of a n-dimensional hypercube of volume 1, for example. But for the permanent, there's no like simple geometric interpretation. But the reason, okay, I'll tell you why we care about this later. But we define the notion of a permanent, and actually, does anyone have any questions about this? Because it's a bit, it's probably a new notion for many of you. The takeaway, it's like the determinant, but you're only adding instead of adding and minusing. Yeah, that's the takeaway. Okay, so now if I have an n by n binary matrix where I let EI denote the sum of the ith row, then I have this upper bound here for the permanence. And, this seems like a linear algebra result. How is this relevant to combinatorics? Yeah. So to tell you that, let's just recall some notions from graph theory. Remember that a bipartite graph is a graph where the vertices can be partitioned into two sets, U and V, such that each edge connects the vertex from U to 1 and B. For a bipartite graph, there's this notion of a bipartite adjacency matrix. We will look at an example of this shortly. That's the definition of it, but the definition will make more sense once we look at the example. Okay, but given a bipartite graph, where the two sets U and V have the same size, a perfect matching is a subset of edges such that each vertex belongs to exactly one edge in the subset. So again, I'll go through an example shortly. But the main point is that this permanence is exactly equal to the number of perfect matchings in the bipartite graph G, where A here is the bipartite adjacency matrix of our graph. And so what Bregman's theorem tells us is that it gives us an upper bound on the number of perfect matches in a bipartite graph. Okay, so this might be a bit abstract at the moment, but I borrowed this lovely example from Wikipedia. I'll let you look at that for a second. I'll explain what's going on. So first of all, on the right-hand side, that's my bipartite graph G. And the red edges, that's an example of a perfect matching. So it's a subset of the edges such that each vertex is covered by exactly one edge. And then this is the bipartite adjacency matrix. So if you recall, in a regular adjacency matrix, it's symmetric. You can observe that here, this one isn't actually symmetric. So if I look at the vertex V1, it has edges to W1, W2. That's why it's 1, 1 here. V2 has edges going to W1, 2, 3, and 4, and so on. So it's sort of like a corrected version of the adjacency matrix, where it tells you from V, so V represents this left-hand side here, which vertices W can you reach. Okay, and then if you actually calculated this quantity here, if you calculated that for this matrix, you would get 20. And what that tells you is that there are at most 20 perfect matchings for this graph. And just a note is that we have, so Bregman's theorem, it's an inequality. And the note is that we have equality when the bipartite adjacency matrix consists of diagonal blocks of ones. So what does that look like? So for example, here, I have like a little diagonal block of one, meaning that between V1, V2, W1, W2, I have all the edges present. So that's like sort of what it looks like. And you can imagine that if I had more blocks of ones, it would be like little sections where everything is connected together. Would we want to take like a 5 minute break or something? Or yeah? Yeah.
So I didn't catch this before, but I guess put this on is something that may not have seen. Like I mentioned.
Yeah. Okay. Yeah, so just a reminder, so like bipartite graph is one where like you have two sets of vertices such that all the edges go strictly from a vertex in one set to the other. And here, a perfect matching just means that I want to choose some of these edges such that each vertex is like sort of hit by exactly one edge.
Some people, of course, inherent all advantages.
Yeah. You can think of it in different ways. Yeah, we'll take like a few minutes break.
We're picking up pizza right now.
Yeah, okay.
We'll wait until you finish.
Yeah.
What's yours? We are What's your podcast? From the sun. She might have almost fun. Yeah, so you do. The originator is all at heart. Yeah, we're fucking.
And it's more reasonable than taking by 9 for 2 months today now. Yeah, that's the whole that yeah, because he's like, I don't know how to Austria, it's gonna slide on 20 people, but not yeah,
Oh,
yeah, not sad holidays. I think 3 hours in one, but it's not. I think that it's the same, that the algorithm is correct. It's like for the solution is greater than the technique, like what your solution, the solution is greater than the odds. So if you have one bad, or think that's you're really going wrong.
you know, stop. What would you do? Why do you start?
Yeah, that's real. $5 on the season, even pricing shows. Yeah, the mouse options are like saw that I'm not going through the stuff.
He was start like revisit, but I know it's just not. It's just great for sequence functions on that, they're like
They're not more like best. I did works with that in the past. Yeah, so these numbers will not change it, I guess. Oh. Okay, so I'm probably just gonna add like these questions. That's what example like. Yeah, I'm sure there is, but this is the only one I'm familiar with. Yes. Because this was all originally formulated like outside of combinatorics, right? It's like a linear algebra solve. And it was originally proved in a really complicated way. That was the yeah. I think even the entropy way of proving it isn't that polite at all. Well, this is yeah, we're just covering the proof of this and then doing the recap. Yes, maybe when we partition. Yeah. On the you finish it. Roughly. Yeah. So can you answer the like you change the language for you? I think oh, see what yeah. I don't think it's mathematicians here, but that's calculated. Yeah. These slides says just as a way. It's only talking just as this um this is more nein, diese Zeit into the defense out, into the piece of that. I'm part of the people. Something more. HDR student. Oh, oh. So we saw. Yeah. Oh. Okay. And like operators here. Yeah. So like combining the two. Yeah. Mostly like the computational side. Yeah. Okay, well, we work here. Yeah. You're working on that now.
Are you gonna use it for what? Well, it's the size of the end of it.
Yeah,
There we go. Just to lead into future numbers.
yeah, yeah.
Semi.
Yeah. So talk a bit of it. I'll talk a bit about the general framework we sort of use when we try to use entropy to solve these problems. So if I have my family F of multiple objects, I try to sample X uniformly randomly from it so that I get that entropy of X is the log of the size of my family. And then I want to express X as a vector of random variable of sorts. And choosing the right encoding will depend on the problem. And it might not be obvious what you're trying to, or what your like definition of X or like how you encode it should be. And then, given I've expressed it as a random vector, I want to decompose it so that I have the entropy of my random vector bounded by the entropy of these sort of local views or projections using either a combination of subadditivity and chain rule or using the Shearer's lemma. And then, as we saw in the ECCR, then once I sort of decompose my entropy into the entities of these local views, I want to use like the constraints of the problem to bound the entropy of each local view. Once I have a good bound there, you can sort of like recombine all your inequalities and then take the exponential to ultimately get a bound on the size of the all bound. So this is like sort of the general recipe for entropy-based proof in combinatorics. Of course, like the particular way you perform each step will depend on the problem, and sometimes the right choice or right way of doing each step might not be obvious. It will require some creativity, a lot of GPT prompting to get you the right formulation. And then, so if we return to our proof of the discrete Loomis-Whitney inequality, in this case, it was like sort of obvious what to do. So I have my family F. I sample each random vector uniformly. Each component here corresponds exactly to each A here. And then the way I decompose my random vector into these local views, here we're not really decomposing, we're like creating a cover. I'm covering my random vector with these n-1 dimensional projections, and then I can use Shearer's lemma to get this inequality. And then to bound this entropy, I use my so-called uniform bound, where remember this is just the size of my projection obtained by deleting the ith coordinate. And then once I combine all of these inequalities, take the exponential, I get the result. Okay, and then the proof for Bregman's theorem, it will follow a similar pattern. So I'll just like show this for now to show you that it follows a similar pattern, but this won't make sense just yet. Okay. And then before we try to prove Bregman's theorem, let's just quickly look at what it said again. So if A is a n by n binary matrix and Bi is the sum of the ith row, then the permanence of A is at most that product, and within a combinatorial context, the permanent of A is equal to the number of perfect matchings in a bipartite graph. This example, actually, one thing which I might write, so I can write that permanence of A is at most. So if we look at our formula, so DI, that's the row sum. So this will be at most 2, check. Okay, 2 factorial to the power half times 4 factorial to the power 1 and 4 times 2 factorial to the 1 and 2, and so on. So just to give you like a concrete idea of what that previous formula actually looks like, I'm looking at the sum of the ones in each row, I'm taking the factorial, and then the 1 over bi power of it. Okay. Oh yeah, and then I had explained here that the permanence is equal to the number of perfect matchings in a bipartite graph G. And then this is the sort of explanation of why. So remember, the permanence is given by this formula. Remember that sigma I, it tells you for the ith row sort of which column to match with. So in this example, sigma 1 will be equal to 2, telling you to match the first row with the second column. Sigma 2 will be 1, you're matching the second row with the first column, and so on. Okay, that's what sigma does. It tells you for each row which column 1 do you want to take. Yeah, and then within the context of a bipartite graph, the row tells you which vertex you're looking at in your left-hand side, and then the column tells you which vertex you're trying to match it with in the right-hand side. So for example, the fact that sigma 4 is equal to 5 tells you that I'm matching the fourth vertex on my left-hand side with the fifth vertex on my right-hand side. Yeah. And notice that we can only match that vertex in U with that vertex V if the corresponding entry in the matrix is equal to 1. So for example, I can't match the fourth row with the sixth column because it's 0 here, and it's 0 because there's no edge between the fourth vertex here and the sixth vertex here. So in order for my sigma to be a perfect matching, then that means I need that entry to be 1 for all n of them. And if all those entries are 1, then the product will equal to 1. The product of all these entries is 1, if and only if each entry is 1. So if I'm summing over all matchings for which there does indeed exist an edge between every header I'm trying to match, then this will give you the number of perfect matchings. Any questions about that? Yeah, so just a recap before we move on. Sigma, it tells you for each row which column you're trying to match with. The rows correspond to your V vertices here, and the columns correspond to your W vertices. You can only match them if there's a 1 in the corresponding entry of the matrix. Okay, so let's try to prove Bregman's theorem. This first proof is going to fail, but it's a useful exercise nonetheless. So I fix my matrix A, and then I let M denote the set of all valid permutations. So these are the permutations which induce a perfect matching. And then I'm trying to sample my sigma uniformly randomly from this set of valid permutations. Yeah. So now I have my sigma. I'm going to decompose it into a random vector. And each component in my random vector it tells me which column to match the corresponding row with. Okay, and then I can use remember, sigma is a random variable, and each of these sigma i's, they're also random variables. So I don't know originally which row will get matched with which column yet. Okay, but you'll notice that once I match a row with a column, that column, it can't be used to match with any other rows because sigma is a permutation. We want to match each column and row exactly once. Okay, so the entropy of sigma, if I use a chain rule, it's the first I look at the entropy of how I match my first row, and then once I match my first row with some column, I look at my next row, try to match it with some column, and so on. Okay, let's try to bound this, for example. So I can use dropping conditioning to get this upper bound on this conditional entropy. So just remember, this is saying the entropy. So I'm trying to match my ith row with some column, given that I already matched all the previous rows. Well, what if I just forget about how I matched all my previous rows? And then this is at most, I use my uniform bound again. This is at most the log of the support of sigma I, where the support of sigma I is telling you the set of columns used by row I in at least one valid permutation. Okay, so there's a subtle point here. And I claim that this is a subset of the columns J for which Aij is 1. And I'll explain this point a bit more, because it's a bit subtle. But ultimately, if I use this as an up down for this, and then I combine it, I ultimately get this. But this turns out to be a really bad upper bound. It's the worst case upper bound. And then the problem here is that by dropping conditioning, we're pretending each row has DI choices, when in reality it has less. What I'm saying here is that I'm acting as though all the ones in my row are possible columns that I can pick at my current step, but at a previous step, maybe an earlier row already used that column, so I can't use it now. But by dropping the conditioning, we're forgetting about all the history, and we're acting as though I could pick any of these columns for which it's 1. Yeah. And then this point regarding the distinction between the support of sigma I and the row sum, if we look back at our matrix here, so for example, suppose my sigma 3, suppose I matched my third row with the second column. It could be the case that there is no perfect matching where the third row is matched to the second column. So even though this is equal to 1, it could be the case that this doesn't extend into a perfect matching, because maybe some other row needed that 1. So for example, if V4 only had a 1 here and 0 elsewhere, if I took that 1 in the previous row, then I have no choices left here. So sort of the ones tell you where you could potentially go to form a matching, but not all the ones will extend into a perfect matching. So that's why I make the distinction between the support and DI. So the support tells you the columns where there's a 1, and it actually extends into a perfect matching. And then this is a subset of the columns where there is a 1. So it's a bit of a subtle point with that, but it's not too bad or too important, but because we're just using it as an upper bound. And then I have an example here. Okay, so suppose so row 4, I have these 4 ones. And like it can be checked that actually there is at least one permutation where, or one valid permutation where I match my fourth row with any of these columns. So each of these columns for my fourth row would be extended into a perfect matching. You can check that yourself if you want to. Okay, so in this case, my D4, which is my sum of my fourth row, is 4. So I know that its entropy is at most log 2 or kilometers 2. Okay, suppose I reveal my first 3 rows already. So in my first row, let's suppose I match the first column, second row matches the second column, third row the third column. Then by the time I'm processing my fourth row, these 2 ones are already taken. I can only look at these 2 ones. So in practice, when I'm processing my fourth row, I can really only choose between 4 and 6. And the entropy of that is at most 1 bit. So the key point is that by dropping the conditioning, we're overestimating the true entropy of this row at the time we're. Any questions about this? Does that sort of make sense what I'm trying to get at a high level? Yeah, it's basically if you drop the conditioning and you forget the history, then you're like overestimating the entropy at each step. Okay, the key insight from Radhakrishnan was instead of revealing the rows one by one, you want to reveal them in a random order. Okay, so it's not like immediately obvious why that would help, but it turns out it does. So what we'll do now is we will consider another uniformly random permutation tau. This represents the order in which we reveal the rows. And this is also sampled independently of sigma. And the sigma is telling you for each row which column to match with. Tau is telling you the order in which to process the rows. And going forward, we'll say that I appears before j if tau I is less than tau j. That just means we reveal row I before revealing row j. Okay. And then I define ni to be in the number of ones in a row that do not lie in the same column as some entry that comes before it. So you can think, let's base on this. Let's just say I wrote 4, I have some ones here. But let's say like in a previous row I chose 1 already from the first column. Some other in my first one here I chose 1 already. So here ni is equal to 1. So even though I have 3 ones, if I've already taken 2 of these ones in 2 previously revealed rows, then I only have 1 left. And then we're not doing this sequentially anymore. So for example, there could be a row or 1 here, like the last row, but I might have processed this before my current row 4, and ni will still be 1. So this is sort of the number of readily available choices for sigma I before it's revealed. So for example, let's just say I have another one here, and ni is 2. So, well, I know I can't use these 2 columns because they were taken by rows revealed before me. So I can only use these 2 ones which haven't been taken yet. But it might be the case that one of these ones don't actually extend into a perfect matching. So it could be that ni is 2, but the sigma I, or the support of sigma I is less than 2. Yeah. So if I have a fixed count now, so I'm revealing the rows in some particular way, then I can use the chain rule again, except instead of iterating from 1 to n, I'm iterating based on the order in which the rows are revealed. So each time I'm processing the entropy of a row, I condition on all the rows revealed before it relative to the ordering given by tau. Okay, and then I claim the uniform bound gives this. So if you recall, really there's like a listing equal sign here. This is equal to the expected size of log 2 of the support of sigma I condition of everything else. And support I is the one that actually extend into a perfect matching. So remember, for this example, maybe I can take this column down and extend into a perfect matching, but this one doesn't. But since I'm using upper bound, I can use ni. So I use the 2 here instead of 1, which maybe is actual support. So I'm sort of being optimistic and like treating it as though every one of these remaining ones can extend into a perfect matching. I'll go for an example now. Okay, the example comes after this, sorry. Okay, so I have this by the chain rule, and this, remember, this is for a fixed tau. And then each of these are my local views now. And then I have this up and down for each of my local views. Okay, and remember, I'm choosing tau uniformly randomly. So from all possible permutations. So I'm taking the expectation now with respect to tau as well. And then the claim is that for a fixed sigma, so if I'm matching each row with some column in some way, then so the way I match the rows of the columns is like sort of fixed, but the order in which the rows are matched, that varies uniformly randomly over all possible ways. Then the claim is that this ni, the number of ones available at the time of revealing, it also varies uniformly over bi. I'll explain this shortly. Okay, so I'll just reveal this for now, but then I'll explain what's happening here. Okay, so I'm looking at my fourth row, for example. There are 4 ones, so it means that there are 4 rows which will use one of the columns here for which there is a 1, and including my current row. So I'll give a more concrete example shortly. But so let me summarize. So there are 4 columns for which there is a 1 here, which means that there are 4 rows, including my current row, which are sort of like competing to take one of these columns to get matched with. And okay, out of those 4 rows which are competing for these spots, if I'm the first out of those 4, then I'm free to choose any of these 4 columns to match with. If I'm like the last one out of those 4, then there's only going to be one of these ones available for me to match with. Okay, so I have an example. Okay, let's suppose this is my by parts adjacency matrix or whatever. Sigma is just this. So I'm matching 1 with 1, 2 and 2 and so on. Okay, so if no rows have been revealed yet, then I can take any of these 4 columns to match with. So n4, so my n is 4. Okay, if row 1 has already been revealed and it took 1, then I can only match with these 3 columns. If row 2 has also been revealed and it took the second column, then I can only use this 4, 4, 6 column. And if rows 1, 2, and 6 have all been revealed and they took the first, second, and sixth column, well, I can only match with the 4th column. So the main takeaway is that the point in time in which we process a row, it will determine or upper bound how many choices we have to map a column with that row. Any questions about this so far? It's okay as long as you follow like the sort of high level idea that you want to reveal the rows randomly, and that will ultimately decrease the entropy once you take the average. Okay, and then the key idea was that since my tau is chosen uniformly randomly, then the relative order in which rows 1, 2, 4, and 6 are revealed is also uniformly random. So there are like 4 possible outcomes here. The claim is that each of these possible outcomes are all equally likely. So each of these possible values for ni are equally likely. So row 4, it has the 1 in 4 chance of being the first one to be revealed out of those 4 like contending rows, in which case n4 is 4, and it's similar for the other cases. So the expected value of the log of n4, so n4 has a 1 in 4 chance of being each of these outcomes. So this is its expected value. So if we drop all the conditioning, remember, our previous upper bound was like 2 bits but now since we're like averaging out, our number of bits is a lot smaller than 2 here. And what you'll find is that this, for any fixed sigma, the same argument applies, and you get the same like equality here. So even though I'm conditioning on sigma, you'll see that this result here doesn't actually have sigma involved. That's because it's going to be the same for every sigma. Okay, we're almost done. Okay, so this is just what we have in general. We generalize our previous observation. Okay, and then now we're going to combine all the inequalities. So remember, my entropy is at most, I'm taking the average over all sigma and tau as they vary uniformly. And then I'm going to like do this expectation in 2 stages. So on the inside, I take the expectation, or on the outside, I'm taking the expectation with respect to sigma. So that means for each fixed sigma, I take the expectation with respect to tau. So we saw that this quantity here, it doesn't actually depend on sigma. It's just equal to this in all cases. So we have that. And then finally, if we like combine this together, and then you take the exponential of both sides, you get Bregman's theorem. Okay, so that's the proof. I know there's like quite a few technical details in there. You can review some of them in your own time. But the main takeaway is that you want to reveal the rows in a random order. You don't want to just drop all your conditioning, because then you're going to overestimate your bounds. Yeah. Okay. So to summarize, these are sort of the 5 steps that for solving certain combinatorial problems using entropy. The proof of the discrete Loomis-Whitney inequality, it followed that format. And Bregman's theorem, the proof, it also followed that format. It's just like, I guess, not as clear. So N is my set of valid permutations. I'm sampling my sigma uniformly randomly from it. Okay, and then I'm decomposing it into these components, sigma I, which tells you for row I which column you're matching with. And then if I'm using the chain rule in a clever way, so revealing the rows in a random order, I get that. So these are my local views. Each one here is my local view. Yeah. And then I use the combinatorial constraints of the problem to get this upper bound on each local view. And then I can combine all these inequalities to prove Bregman's theorem. Okay, almost done. Some closing remarks. So we define the notions of entropy and conditional entropy. Of course, there's more to the study of like information theory. There's other concepts like mutual information, chaotic divergence, which we didn't cover today. We equipped ourselves with the main tools. So really, we only have like 4 tools. We have subadditivity, Shearer's lemma, chain rule, and dropping conditioning. But But there's also many more tools which we didn't cover. For example, we have like conditional version of all those tools we just mentioned. But even with just those 4 tools, we could prove 2 like really non-trivial results with elegant entropy-based proofs. And okay, we only covered 2 main examples today, but I'm sure there are other like hundreds of beautiful applications of entropy in combinatorics. Okay, and then these are some resources I recommend if you want to learn more about entropy in combinatorics. They were very helpful in the development of these slides as well. And that's all. Thank you, everyone.
And questions and guidance. Have you used these much in your own research?
Yeah. So it's sort of why I got interested in this was I came across some paper where, well, I'm not going to go into the specifics of the problem, but like they proved some result in like say 3 dimensions. But sort of if you wanted to generalize the result to n dimensions, the natural way of doing that was using Shearer's lemma. So that's how and so I started looking into like entropy stuff. Because at the time I wasn't familiar with Shearer's lemma. So it does pop up.
All right, so thank you again for this wonderful presentation, Jeffrey. I hope everyone enjoyed. If you haven't yet, please scan the QR code. For those that are watching on the recording or online now, I'm going to end the stream. Thank you also for watching. So now, of course, you can smell the pizza if you are here in person. We're going to let you have that now. We do need to get a photo with everyone as well. If you haven't scanned the QR code, again, please do that.